In today's lesson, we will be going over the anatomic structure. When we look at the chemical level, we need to look at the chemistry, which is going to be the science that deals with the structure of matter. This is going to include the structure of the atoms, the basic chemical building blocks, how atoms combine to form increasingly complex structures. We're going to start off with the atom, and then we're going to grow into different types of molecules, and then we'll continue on into the different types of macromolecules that we'll see in anatomy and physiology, including proteins, carbohydrates, nucleic acids. We know that matter is anything that takes up space and has mass or has weight to it, and this is going to be made up of atoms. These atoms come together to form different chemicals with different characteristics, and we'll look at what makes each atom different and how they're going to make different chemicals based upon those atoms. Chemical characteristics are determining the physiology at the molecular level and cellular levels. Subatomic particles are going to help to understand the properties of matters. We're going to see that these subatomic particles are going to include our protons, neutrons, and electrons. Protons, we want to remember, are positive. They are going to be located in the nucleus. They have a mass unit of 1, so they are going to have weight to them. Neutrons are going to also be located in the nucleus. They are going to be a neutral charge. They don't have a charge. They are going to be neutral. And they are also going to have a mass unit of 1. Electrons are a little bit different. They're going to have a negative charge. And if we notice, they have a very low mass. They're also not in the nucleus. They're actually going to be outside of the nucleus, located in what's called the electron cloud, which we'll see in the next few slides. So from this slide, what we want to remember is protons are positive. They are located in the nucleus, as well as neutrons are located in the nucleus. Neutrons are a neutral charge. They don't have a positive nor negative charge. Both protons and neutrons have a mass unit of 1, giving the atom weight. And electrons are going to have a low mass. We don't need to memorize the mass unit here. Just understand that they are so light that they are going to be floating around outside the nucleus in this electron cloud, and they are a negative charge. This is what we can see here. So if we were in class, I would ask you, what 2 subatomic particles are located inside the nucleus? And your answer would be protons and neutrons. And here we can see the electron cloud, where these electrons would be moving around like this in a way where they would be near the nucleus. They have a negative charge. They are located outside of the nucleus, whereas protons and neutrons are located inside the nucleus, and protons are positively charged subatomic particle, and neutrons are a neutral charge. What does that mean? When we look at the atomic structure, we're going to see that the number of protons in an atom equals the number of electrons. We said the nucleus is going to contain both the protons and the neutrons. Our atomic number is going to be the number of protons. This is going to be shown on the lower left corner of the periodic table, and that's going to be determining our element that we have is going to be determined by the number of protons. So our atomic number gives away the characteristic of that atom. Our atomic mass number, because we had previously stated that the atomic mass number of protons was 1 and neutrons was 1, this is going to determine the mass of the entire atom. Since the electrons are such light weight, they don't have a lot of mass to them, they're not going to contribute to this atomic mass number. If we take a look here, we have carbon, and if we were in class, I would ask you, how many protons does carbon have? And we would look at the atomic number here, and we would notice that there is a number 6, which indicates there are 6 protons in carbon. And this is giving our atomic number. And also, if we look at each element here, hydrogen has 1 proton. Over here to the right, helium has the number 2. Its atomic number is 2, which is 2 protons. And we continue 3, 4. Each element has a different number of protons, and that also indicates a different atomic number. When we look at the mass number at the top left corner here, we can determine how many protons are in this element and how many neutrons are in this element. So the atomic mass number is the number of protons and the number of neutrons. So how do we figure that out? We take the number of protons, which was our atomic number, and subtract it from our atomic mass number. That would give us the number of neutrons, which would be 12 minus 6, which would equal 6. We have 6 protons that was given to us by our atomic number, and we subtract the number of protons from our atomic mass number, which is 12, and that gives us the number 6, which is our number of neutrons. The other statement that we saw previously in the slide was that the number of protons is also going to equal the number of electrons. Here we could see 2-4. This indicates that we have 2 in the first shell and 4 in the second shell. So 2 plus 4 equals 6, which also gives away how many electrons we have. And we'll discuss this a little bit further as we continue in this lecture. If we were to give another example, over here with helium, our atomic number is 2, which is our number of protons. Our atomic mass is our number of neutrons and protons. So 4 minus 2, which is our number of protons, gives us our number of neutrons, which is also 2. And those are just simple mathematical equations that I'm giving as examples, but we can apply this to any of these elements in this chart. So understanding the atomic number is our number of protons, our atomic mass is our number of protons plus our number of neutrons, and those are both in our nucleus. And the other rule that you want to remember is that the protons are going to equal the number of electrons as well, although we're going to see in the future within this lesson that our atomic mass number can change because our number of neutrons can change, and our electrons can also change. Our atomic number is never going to change. We're never going to see a different number of protons in our element because that's determining that specific element. So we could see the atomic mass change or the electron configuration change, and we'll discuss that as well. The electron cloud is known as a spherical area that contains electrons, which is what we saw previously in the previous picture. But when we draw a two-dimensional representation of this electron cloud, it's called an electron shell. So we're going to see that there are multiple shells within this electron cloud. Here we can see how many elements there are in the human body, but what is most important for us at an anatomy and physiology level, we're going to see that oxygen is found in the body, of course, carbon, hydrogen, nitrogen, calcium, phosphorus, potassium. For right now, you don't need to memorize the significance, but just understand that these are readily found elements in the body. We also have principal elements that are going to be a little bit less percentage in the body. In the bottom of the table, we're going to see sodium, chloride, magnesium, sulfur, iron, iodine. And then there are these trace elements that some of these can function as cofactors, helping with chemical reactions and metabolism. These are the main ones from the previous slide that we want to know, since we're going to see in the future in anatomy and physiology too that these are going to play a role in our different chemical reactions and metabolic reactions within the body. And remember, metabolism is the sum of all chemical reactions in the body. So we're going to see hydrogen, carbon, nitrogen, oxygen. Here, if we look at P, this is going to be P for phosphorus. K over here is potassium. K comes from the root word kalium. That's why we say represent K for potassium. We have sodium, magnesium, calcium, iron, and iodine, chloride, sulfur. This previous slide where we could see the representation of the letter and the element's name. I do want you to remember this and memorize this. It'll help you in the future with subsequent lectures. An element is a pure substance composed of atoms of one kind, meaning that the atomic number is the number of protons and it determines its chemical properties. As we saw previously on that periodic table, that we had a different number of protons and each element had a different atomic number. So this is going to change and determine its chemical properties. So calcium is going to present differently with different chemical properties than sodium, and hydrogen is going to present with different chemical properties than oxygen. So each element contains a different atomic number, but as we stated previously, some things can change. For example, the mass number, this is called an isotope, which is a different version of the element based on the mass number. Our mass number was the number of protons plus our number of neutrons. Only the neutrons are different because the number of protons is determining that element. We could see different types of hydrogen, for example, or oxygen, which are going to be called isotopes, where our protons are going to remain the same, but our mass number, our number of neutrons, can vary. So radioisotopes here at the bottom, these can release radiation. Weak radioisotopes are used for diagnostic imaging like X-rays. Here we could see an example. Again, in our nucleus, we have the number of protons plus the number of electrons. Here we could see that we don't have any neutrons, so our atomic mass number is going to be 1, since we only have one proton here, and we have one electron in the electron shell. So a hydrogen nucleus contains one proton and no neutrons, but we can find different types of variations, different types of isotopes found on Earth. Another type of hydrogen, an isotope of hydrogen, which has one proton, which we have one atomic mass, and one neutron. Now we have an atomic mass number of 2, and this is now an isotope of our most commonly found hydrogen. Here we have another example. So we have one proton and 2 neutrons. What do you think the atomic mass number would be here? The atomic mass number would be 3. These are isotopes of hydrogen, but as you can see, protons are going to remain the same. We're never going to change the number of protons because that's determining our element, which is determining the characteristics of that element. Now looking at the electrons, our electrons are going to be outside of the nucleus. So electrons in the electron cloud determine the reactivity of an atom. So what does that mean? It means that each shell is going to contain a limited number of electrons. We're going to see that the first shell can hold a maximum of 2 electrons. The second shell can hold a maximum of 8. And the third shell can hold a maximum of 18. We can continue on with this, but again, this is more based for anatomy and physiology. Here we could see the valence shell is going to be the outermost shell that determines the bonding. And we want our elements to be complete. So they're looking for these electrons to maximize their shell so that they become stable, so that they become happy. That's how I like to remind the students. They're looking for another electron, they want to bond, and we'll talk about different types of bonding between ionic bonding, covalent bonding, and they want to search for that electron, whether it's sharing an electron from another element or maybe taking an electron where a electron is donated to them. This is all going to be a part of making them more stable. So for example, here we see in the first shell, carbon has 2, and in the second shell, carbon has 4. So carbon is now looking for 4 more electrons in that second shell so that it can become complete. We can also see For example, over here, we have our noble gases. These are all going to have a balanced last shell. So, for example, here we could see 2, 8, 18, and 8. If they have 8 in their last valence shell, they are complete. Helium has 2 in its first shell, meaning that it's complete. It's not going to be donating or taking electrons since it's already stable and happy. Whereas, for example, chlorine is going to be looking for another electron. So you want to think about, is it easier for chlorine to give away 7 electrons, or is it easier to take and maybe share 1 electron? It's usually easier for them to borrow or share 1 electron in that case. And it depends on the element, of course, where we can see like sodium. If you think of like sodium chloride, table salt, sodium has 1 in its last outer ring, or its valence shell. It's easier for sodium to give up 1 than it is to find 7. So that's where we see sodium chloride, and we'll talk more about that. Sodium will donate and share a electron to chloride, and that's what creates our table salt, our sodium chloride. Here we can see the difference between hydrogen and helium. As we said before, hydrogen has 1 proton, which is our atomic number. Because it only has a proton in its nucleus, it has a mass number of 1, and it also has 1 electron. It's looking to complete its shell, and it's going to be looking for another electron. Whereas helium is stable because it has 2 electrons in its outermost shell, in its valence shell. Here we have another example. So here we have lithium. It has 2 in the first and 1 in the second. The second, it's either going to potentially donate or maybe share another 7 or find 7. It can occupy 7 more in its second shell. And then here we have neon, which is 2 in the first, and we can count 1, 2, 3, 4, 5, 6, 7, 8, making this second ring complete. So its valence shell is complete with a total of 8. Now we're moving on to chemical bonding. There are different types of chemical bonding. We could see ionic bonding, covalent bonding, hydrogen bonding. When we look at chemical bonds, we're looking at the formation of molecules and compounds. The difference between a molecule and a compound is that a molecule is a chemical structure consisting of atoms held together by shared electrons, whereas a compound is made up of atoms of 2 or more different types of elements, different elements in a fixed proportion, regardless if electrons are being shared. So if we think of a water molecule, we think of H2O. They're going to be sharing electrons, and we'll discuss that in a little bit. But first, we want to see, how do we draw these chemicals? We have multiple atoms, we have multiple electrons, protons. Like, how do we draw this on a piece of paper without drawing each individual circle on the piece of paper? So this chemical notation is used to describe chemical compounds and chemical reactions in the body. How do we draw a reaction? How do we draw ions? We're going to see that in the next few slides. So here on the left, we have the visual representation showing 1 hydrogen atom, 2 hydrogen atoms. These are 2 separate hydrogen atoms. This is 1 oxygen atom, 2 separate oxygen atoms. So over here, we can see the chemical notation of how we draw these atoms. The representation would be 1 individual H, an uppercase H, 1 individual O, which is an uppercase O. If we want to determine that there are 2 atoms of hydrogen, we're going to put a large 2 in front of the letter. So 2H would indicate 2 atoms of hydrogen. This indicates that they're not bonded. They're just 2 separate hydrogen atoms, 2 separate oxygen atoms, a large 2 and an O. Here we can now see a molecule where now they're bonded together. Now they may be sharing electrons, maybe they donated an electron. For right now, we can see 2 hydrogens bonding to one another, creating a molecule, 2 oxygen molecules coming together. So now look at the representation on the right. We have H and an O and a subscript of 2 next to it. Over here, water molecule looks like a Mickey Mouse. We have two hydrogens, and we'll discuss why these hydrogens are more biased to one side of this oxygen. We'll talk about the polarity in a little bit. So here we have one oxygen and two hydrogens. This is composed of our water molecule, and over here is going to be H2 subscript 2O. So this is our water molecule. So now we know if there is a number in front of the letter, like 2H, as we saw here, this indicates that we have two separate hydrogen atoms that are not bonded. When we see it written in this fashion, H subscript 2, now we know that these hydrogens are bonding together. Then we continue on with how do we draw reactions? How do we draw chemical reactions within this representation? So if we were to have multiple reactions, it would be difficult to draw out all of these hydrogen circles and these oxygens. The arrow indicates the direction of the reaction. So from the reactants, usually it starts on the left, and then we'll see the arrow is going to dictate what happened to create our product, which is usually on the right. So on the left side, we'll see the reactants. We have two hydrogens. Again, they're not bonded, and an oxygen. And then the arrow is going to indicate the direction of the reaction, and then we see our product. So how can we see this in a chemical notation? We have 2H, meaning that these two hydrogens are not bonded together, plus an oxygen, and then our reaction takes place to then determine our product, which is H2O. This is a balanced reaction, meaning that we had two hydrogens and an oxygen on the left, and then our product also had two hydrogens and an oxygen. This is indicating and showing what it would look like if it was an unbalanced reaction, although this is an incorrect drawing of the chemical notation. So if the reactants have a certain number on the left, the product will have a certain number on the right. If we're removing or breaking down a product or creating a product that we've removed some sort of water molecule or added a water molecule, we'll also see that on the right side of the product, but it needs to be indicated that it was removed or added. Then we have what are called ions. This is going to be a superscript with a plus or a minus sign. So here, again, our example that we could see, we have sodium. Sodium has 1, 2 in the first shell, and then 1, 2, 3, 4, 5, 6, 7, 8 in the second shell, which is a complete shell, and then 1 in the last shell, which means that it's looking for another 7 to be complete, or potentially can hold up to 18 in the third shell. So in this case, sodium, it's easier for sodium to remove the hydrogen and allow it to go to another element. So it would be easier for the sodium to lose an electron rather than to gain 7. In this case, we remember that the electrons are negatively charged. So if we lose negativity, maybe you have someone that's a very negative person. If you lose that person, then you become more positive. So if you lose negatively charged subatomic particle, you become more positive, right? Sodium is losing an electron, and here we could see it became more positive. It gave up an electron. That's what we could see. The superscript is a plus next to the element. So that's the visual representation, but how we actually draw it out in chemical notation is Na+. That indicates that we've given up an electron. What do you think about chlorine here? If we have more of a negative charge, that means that we gained an electron, right? Because electrons are negative. If we gained an electron, now we become more negative. And again, I just give the example of if someone's negative in your life and you no longer are associating yourself with them, you become more positive. So I just give that as an example, but you can think of it in the normal sense of electrons are negatively charged. If we lose an electron, the sodium ion became more positive. It lost one electron. Chloride has now gained an electron. Over here, calcium, because we have 2 superscript plus, that means we lost 2 electrons. We become more positive. We've given up 2 electrons in that case. With our chemical bonding, we have different types of chemical bonds. We can either gain an electron, as we saw before, we can lose an electron, or we can share electrons. So there are three major types of chemical bonds. They're called ionic bonds, covalent bonds, and hydrogen bonds. Ionic bonds, we want to think of gaining or losing an electron. Covalent bonds, we want to think sharing electrons. And hydrogen bonds, we want to remember, are very weak bonds. They're easily broken. Ionic bonds are going to be similar to what we had just seen before, where we see an electron donor and an electron acceptor. One element is going to gain an electron, one atom is going to gain an electron, and another atom is going to accept the electron. Here we could see some examples: sodium, potassium, calcium. This then becomes what's called a cation. Cation indicates that the ion has become more positive. So if we look at the word, cat looks like a plus sign. The T in cation looks like a plus sign. That's one way that we can remember cation is a more positively charged atom now, whereas an anion becomes more negative. And I like to remember anion has an N in it, two N's, so it becomes more negative in comparison to what cation. Cation has a plus sign in it, if that helps you remember it. So ionic bonds are attractions between cations, which are positive ions, and anions, which are negative ions. We have sodium. Here we have 1, 2 in the first shell, 1, 2, 3, 4, 5, 6, 7, 8 in the second shell, and only 1 in the third shell. So it's easier for this sodium to donate and give up its electron to chlorine, which is only requiring 1 more in its last shell to become full. Chlorine has 1, 2 in its first shell, making it complete. 1, 2, 3, 4, 5, 6, 7, 8 in its second shell, and then 1, 2, 3, 4, 5, 6, 7 in its third shell. It needs 1 more to then become stable. As sodium gives up its electron, sodium then becomes a positive, it becomes a cation, a positively charged element, and chlorine then gains an electron, it becomes an anion, it becomes negative. Those opposites attract. Now, these charges, the positive of sodium and the negative of chlorine, now draw these two together like magnets because opposites attract, and that's where we see this ionic compound. Because sodium and chlorine have opposite charges, they are attracted to one another, and the association of sodium and chloride form the ionic compound sodium chloride. Here we could see the 3D representation of what is table salt. The large number of sodium and chloride ions form a crystal of sodium chloride. Now moving on to covalent bonds. Covalent bonds, not all atoms will gain or lose electrons to become stable. These are going to actually share electrons, whereas before we saw ionic bonds losing an electron or gaining an electron. Covalent bonds share the electrons. So some atoms can complete the valence shell by sharing these electrons with other atoms. Covalent bonds are strong bonds. 1 electron is donated by each atom to make the pair of electrons. We'll see that this is represented by a dash. We'll see that covalent bonds, a single covalent bond indicates a sharing of 1 pair of electrons. Double covalent bonds are shared by 2 pairs of electrons, and triple covalent bonds are shared by 3 pairs of electrons. What does that mean? This is that bond right here. So this line, this pairing, this bonding, this indicates that the 2 hydrogens have come together and they're sharing an electron. So this electron can be from this hydrogen and this electron can be from this hydrogen, which indicates that now the hydrogen on the left has 2 electrons, making it stable, and the hydrogen on the right has 2 electrons as well, making it stable. So this is what is shown as a covalent bond, a sharing of electrons. Here we can see another example. This oxygen has 1, 2 in the first shell, and it has 1, 2, 3, 4, 5, 6 in the second shell. It needs to have 2 more to become complete in its valence shell, which is going to be represented by these yellow electrons here that are being shared by the oxygen on the left. Now this oxygen is complete. It has 8 in its outermost shell, and this oxygen also has 1, 2 in its first shell, and 1, 2, 3, 4, 5, 6 in its second shell. So now we have 1, 2, 2 pairs of electrons that are being shared, and that's what is shown as this double bond. These 2 lines that are being shared. This is a double bond, meaning that this line indicates a pair of electrons that are being shared, and this line indicates a pair of electrons that are being shared. And we can see that throughout these other examples down here. Then going a little bit deeper, our covalent bonds can be polar or nonpolar. So what does that mean? Nonpolar covalent bonds means that there's an equal sharing of electrons between atoms that have equal pull on the electrons. So nonpolar is going to be equal sharing, whereas polar covalent bonds are unequal sharing of electrons because one atom has a disproportionately strong pull on the electrons. So these form polar molecules like water. So that's where we'll see this situation happening, where the electrons on the outer ring of oxygen, they're going to be over here more negative. Over here, hydrogen is going to share an electron with oxygen, and this hydrogen will share an electron with oxygen. And once they share that electron, we'll see that these electrical charges on a water molecule, this would be more positive on this side of the oxygen. This would be more negative. The negative side of the hydrogen is now being attracted to the oxygen. So in forming a water molecule, an oxygen atom completes its valence shell by sharing electrons with a pair of hydrogen atoms. The sharing is unequal because the oxygen atom holds the electrons more tightly than do the hydrogen atoms. So the electron charges on a water molecule, because the oxygen atom has 2 extra electrons much of the time, it develops a slight negative charge, and the hydrogen atoms become weakly positive. The bonds in the water molecule are now considered the polar covalent bonds. It's an unequal sharing of these electrons. And then our last type of bond, we have what are called hydrogen bonds. These are weak polar bonds between adjacent molecules based on electrical attractions. So these involve attractions between a slight positive charge and a slight negative charge. Hydrogen bonds do not form molecules. Hydrogen bonds between H2O, water molecules, cause surface tension. So you might have noticed surface tension is the ability or capability that the water can be attached to a surface. So if you've washed your hands and you notice that water is still adhered to your skin, that's considered surface tension. Here we can see the negative aspect right here of one oxygen is then going to be attracted to the positive aspect of the other water molecules. So this would be hydrogen. Remember from our previous slide showing the nonpolar covalent bonding of water. This aspect of hydrogen is a slight positive charge, as well as this side. So this is attracted to the slight negative charge of oxygen. These red dashes are our hydrogen bonds. Now we see the same thing over here. The positive, slight positive charge of this water molecule, the hydrogen, is attracted, because opposites attract, like magnets, attracted to the slight negative charge of this water molecule. And this is our hydrogen bond. We're going to see hydrogen bonds in the future when we are going to be discussing the different types of protein structures. And we'll see how those large types of proteins are going to be creating different types of structures. And last but not least, we have states of matter. Solid is going to be a constant volume and shape. Thinking of, again, water is another great example. If ice is solid, ice is the solid portion of water, it's a constant volume and shape. If we melt the ice, we now have liquid, which is the water that's going to contain and consist of volume but can change shape. And then if we continue to increase the heat or the temperature in water, it's going to evaporate, which then turns into a gas, and gas is going to change volume and shape.